so this is going to be lecture 4. Actually, before I start, do you have any questions about the midterm or project that you'd like to ask me? Yeah.
What's the best thing to study for? Like, what lecture are you looking for?
So I think I've told everybody, and Kevin sent something out about how it's a take-home midterm. I'll send out my slides at the end of lab today, so you all have that. And I mean, it is take-home, so I would say your best resource probably going to be Google. But other than that, I don't know if Kevin sent out a study guide. I think he was thinking about it, but I don't know if he actually got around to sending it out or making one. But again, take home. You've got the power of the internet. I think you can all do it. All right, so lecture 4. In this lecture, we'll be covering brazing and soldering. We'll be covering some oxy-fuel topics, metallurgy, and the concerns welders have about it, and the concerns the engineers should have while designing objects made of metal that require welding. And we probably won't get around to wire feed process. I was going to see if I could squeeze that in because we're a week behind, but I think that those topics will take till the end of lecture, so that'll be next week. All right, so up until this point, all we have done is welding. However, there are many other ways to join materials. Brazing is a great way to join materials together because it does not actually melt the base material. That is awesome because if you need to join super thin material to super thick material, brazing is your best friend because while you are heating the thin material, it will most likely melt away before you are ever able to heat the thick material to the point where you can weld the two together. And so when you implement a process like brazing, it does not melt either material. It simply adds brass to the surface of both, bonding the two together. And what makes brazing different than soldering is that it occurs above 800 degrees and below 2000 degrees. And that's the main difference, other than the filler material is brass, or certain mixtures of brass like silicon brass. And you cannot braze without the use of flux. That's another difference between soldering and brazing, is where the flux is applied. So as you can see in that little diagram, the flux is applied to the outside of the filler rod, and as you melt the filler rod, the flux melts too, and what its purpose is to clean the surface of the material that the brass is laying onto, because if there are any oxides or like grease or any impurities on the surface, the brass will not adhere properly to the metal itself. So yes, surface finish or surface prep is very important for brazing. You want a clean surface. You can do that by pre-sanding or stripping grease with some kind of solvent, but it needs to be clean. In a lot of cases, brazing will actually be stronger than welding. While brass does have a lower tensile strength than steel, on thin material, if you are welding it, you are going to be creating a heat-affected zone on either side of the weld. And that heat-effective zone has lesser properties than the base metal itself. It becomes weaker after the welding process. And so even if you have a really good weld, and it's a really strong weld, when you go to do a tensile strength test, the base material will shear or rip in the heat affected zone and your weld will be left unaffected. However, with brass, because you are not reaching the melting temperature of steel, or with brazing, you're not reaching the melting temperature of steel, when you lay it down, it does not create a heat affected zone, so you can weld ultra thin or braze ultra thin material, and it will retain its strength after the process is done. And the way you get it to be as strong as the steel itself is you lay down a thicker bead of brass, and still the steel will often break within the steel and not the brazed joint, because the braze will be stronger than the base material itself. It is also very good for joining dissimilar metals. I won't say you cannot weld aluminum to steel, but it is not commonly practiced, and it takes very specialized equipment in order to do it. But anyone can braze aluminum to steel, because you are just using a third-party metal to join the two together. You are not melting either, you are just laying it on the surface. Another application for it is cast iron. Cast iron, you do not weld. If you weld cast iron, the internal stresses created from the welding process will cause cracking on either side of the weld. So what you do if you need to fix a cast iron object is you braze it. Good? Any questions?
How does it stick if it doesn't melt the metal?
So it sticks because there are surface impurities on the metal itself. And you can often get it to stick better by sanding the surface and making it rough. And it will just lay on top of the material, bonding to the impurities themselves. Yeah? So, brazing is done 3 common ways. Oxy-fuel brazing is the most common way it is done. So that is with a actual torch. We have not used the oxy-acetylene torch in the lab yet, but that will be coming up maybe next week or the week after. It uses a neutral flame, so it does not have excess oxygen or excess fuel to heat the material, not to its melting temperature, but just until the brass will melt, and lay it on the surface. Oxy-fuel brazing is not the prettiest. It is usually hard to control because when you heat with an oxy-fuel torch, there is no localized heating. That's not really possible. The heat disperses into the material. So when you braze, the brass will flow over a large surface of the material, and it is hard to get a clean, small braze joint when you do oxy-fuel welding or brazing. GTAW, so gas tungsten arc welding. This is used when heat is a concern, so you don't want a ton of heat in the entire workpiece itself. You want localized heating and a localized brass joint. It's very commonly used on stuff like bike frames. So if I've got any people who are very into biking or in any biking clubs, if you wanted to weld your own frame or braze your own bike frame because you wanted certain properties or you wanted it to be super light, brazing is something you would choose because you can pick ultra thin material. You don't weaken it when you join the two pieces together, and you would use gas tungsten arc welding or TIG essentially to do those joints. And in this previous picture was a bike frame that had been TIG brazed. That's what it looks like. It is nice and clean. It looks just like a weld, but it is just brass. And again, you're not melting the base material. And then you got gas metal arc welding, which is MIG. So the difference between gas metal arc welding when you're doing brazing is just the wire spool. You put on a brass wire spool and then you lower the voltage and wire feed way down. So you are laying down material in a much more controlled manner. You are not melting the base material, so it takes place at very low voltages. It is very common in the automotive industry, or if you are doing anything with tempered metal and you do not want to change the properties of the metal itself, you can use gas metal arc welding and join those pieces together. When you do this, you do use shielding gas because you do want to protect the brass from oxygen. And so you use 100% argon in both gas tungsten arc welding and GMA and oxy fuel. So that you can't add an external gas to, but when you use a neutral flame, it is burning all the oxygen in the flame, and so there is no excess oxygen in the weld or the brazed site for it to grab onto. Soldering, it's a little different. I don't have a ton of slides on this, but most of you will probably solder at some point in college when you take electronics class. It takes place below 840 Fahrenheit. That's the difference between brazing and soldering, or one of them, and the flux is applied to the joint prior to the solder. And the flux serves the same purpose. It cleans off any oxide layers or impurities on the joint, allowing the solder to form directly to the copper, which is what you usually do, although jewelry making uses silver solder when joining small pieces of jewelry together. And surface prep is very important. So generally, if you're going to sweat a pipe, what you do is you get a wire brush and you clean both surfaces very thoroughly, so it is just pure raw exposed copper, and then you're able to solder that joint. And it is often done with a propane torch, not an oxyacetylene torch, because it is a much cooler process. Or a soldering iron, as you all probably know. So, oxyacetylene. There are several different flame types for an oxyacetylene torch, and each one serves a different purpose. You can see up in that table the amount acetylene to amount oxygen you use. It is the ratio between them that causes the flame to behave a certain way. But the three mainly used flame types are the carburizing flame, neutral flame, and oxidizing flame. The fuel flame, which is the first flame you get, is rarely used, although I will go over one application right now. So, like I said, it is hardly used, although it can be used as a preheat indicator. So, the fuel flame is super sooty because it often, or it does not burn off all the acetylene. There is some acetylene left unburned. So if you use a fuel flame, it will be laying down a ton of soot on whatever you're pointing it at. So it'll just leave this black burnt look, even if it's not actually burning it. And what that is unburned fuel laying on the surface. And so when you want to reach a certain temperature, and it's around 500 degrees or 550 degrees, you can then move to a neutral flame and begin heating the object. If you want the object to be uniformly heated, you cover the whole thing in soot, heat it so that all the soot gets burned off of it. And once the soot is all burned off the entire object, you know that the object is now at 550 degrees, which is very useful for certain welding processes when you want to keep stuff like hydrogen out of your weld, which is caused by water being on the workpiece itself or trapped within the workpiece, and you can preheat it to get rid of all of those impurities that can cause cracking or a bad weld. It has also been used in the past, not very commonly anymore, but for a specific paint effect. After you paint the object you want this effect on, before the clear coat, you will turn on the oxyacetylene torch to the fuel flame, and then you can put a soot pattern onto the paint by briefly waving the torch over the paint job. You got to use certain kinds of paint for this, but it will leave soot patterns on the paint, and then you clear coat that, and the clear coat layer will absorb the soot and preserve it, and you get a very specific look. The carburizing flame. So this is used a lot more, but it adds carbon. So still there is unburned acetylene in this flame, but that is good. It's using oxygen. It's a much hotter flame. And what that carbon does is it does something called hard facing, which is simply adding carbon content to the surface of a material while you weld or braze, and that hard facing causes the exterior shell to be significantly harder than the material below, so you get this protective layer. It is commonly used on like boring heads when joining the tungsten carbide to the metal behind it. You would use a carburizing flame because the tungsten carbide is super hard, but the thing holding the tungsten carbide on is not necessarily as hard as the tungsten carbide, and so to prevent wear, you use a carburizing flame, and it will put a protective hard shell over the material joining the tungsten carbide to the steel. It is also the brightest of all the flames, and that is one way you know you're in a carburizing flame is as you turn oxygen on, you will see a very, very bright flame segment right as you begin to turn it on. Any questions so far? All right, now we start getting into the cool stuff. So the neutral flame, this is where oxy-fuel welding takes place. It is very common also for preheating, not only welding. But I mean, other than welding metal together, you can also use this kind of flame to heat metal till it's red hot in order to form metal itself. So you can heat it up and then beat it with a hammer into shape. And it produces heat of excess of 6,500 degrees Fahrenheit. And I said this earlier, but the flame itself is acting as the shielding gas while you weld. You cannot make a good weld without shielding gas. And the way this one works is because it is a neutral flame, that means 100% of the fuel and oxygen are reacting together. So there is no excess oxygen within that flame to go into the weld. And because the air is outside that flame, the air is not able to penetrate the weld either. Good? All right, and an oxidizing flame. So this is pretty cool. It's used for cutting high iron content materials. It is after the neutral flame, so when you put an excess of the accelerant, which is the oxygen, into the flame itself, it will cause the iron to start to burn once you hit a kindling temperature, which is around 1600 Fahrenheit. This is how people cut insanely thick steel. As you can see in the picture, they're cutting like 5-inch steel, and they do it with ease. It'll cut through it fast. This will cut through up to a foot of steel. What else do you need to know? Commonly, so the oxy-fuel torch, you don't rely on an oxidizing flame to heat up the material because it is actually cooler than the neutral flame. So you use a neutral flame to preheat to 1600, and then a cutting torch has a special lever on it that allows more oxygen to get dumped through the regulator out of the front of the gun. So once you hit that kindling temperature, which is where the metal begins to glow red generally. You pull the lever, it dumps excess oxygen out of the front of the gun. That causes the iron to ignite, and it begins cutting through by burning the iron away. It is a rapid oxidation process. So after you've established the iron burning, you do not need any heat to continue it going. Just like a fire, you can turn off the acetylene and have no flame coming out of the oxyacetylene gun and continue to cut the iron as you go, because it will self-sustain that burn. I added this in here just because I personally think it's super cool. A thermal lance is an oxidizing flame. However, the actual lance itself is a type of tool that is consumed as you use it. So what it is a massive iron rod. By massive I mean long. And then there is a bunch of what look like filler rods inside of that are also made of iron and sometimes aluminum to add extra temperature. And then oxygen is dumped through the thermal lance because it is a pipe. You then ignite the end of the thermal lance, which starts it burning. And so it is shrinking as you use it, but it can be used to bore through 12 feet of iron or concrete. It can pretty much cut anything. You can see in the picture here that this guy is cutting through what looks like 2.5 foot solid steel stock. In industry, it is mostly used as a demolition tool. So on massive ships or like heavy equipment like excavators and dump trucks, if you have a seized axle or a snapped axle, you can use a thermal lance to bore through the entire axle in order to remove it without damaging like the bearings and the surrounding housings, because oftentimes there is no other thing that can cut through this kind of material. It is used to trench through concrete as well. There are machines that just you push along, and it has a thermal lance pointing at the ground, and it'll move about 1 to 2.5 inches a minute, and it will be cutting a trench about 18 inches deep into concrete. It's thermal lance. All right, so we're gonna start getting into some metallurgy. Real quick, so that is a titanium exhaust pipe, and it looks super cool. The welds look really nice. Those are actually throwaway welds. You would never in industry, unless it's something completely worthless like an exhaust pipe, allow titanium to look like that, because that is like giving a weld to somebody that is covered in rust and has oxidized a ton. The bluing or yellowing means that there is oxygen present while welding it, and you have now compromised both the weld and the titanium's properties themselves. Titanium is one of the harder metals to weld, and so you've got to use argon flooding to protect it, or weld it within basically a box of argon to get rid of all the oxygen present. So each metal, that was just a specific example about how titanium has certain characteristics, but each metal and alloy has unique chemical, mechanical, and physical characteristics that are very important to know. For most purposes, you don't really need to know them. You can just get general mild steel or 6061 aluminum, but if you are in an industry like the aerospace industry, and you are sending things to outer space, or you are in the automotive industry, the relationships that metals and alloys and filler rods have with each other are very important, because if you use one that reacts poorly to the base metal, it can fatigue crack over time and be weak. So these are important things to research. They're not important things to necessarily know off the top of your head because there's so much information out there about these things. It is also important when you're picking material to know the things about the material before you begin designing, because oftentimes you will design things that cannot be built or should not be built if you do not understand the material constraints. So, the basics. The heat affected zone is something you all should know about. This is any time you have a weld, there will be a heat affected zone. Even on a super precise laser weld, there is a heat affected zone. And so the heat affected zone is this area surrounding the weld where it is base material that has been affected by the heat but does not have weld on it itself, because oftentimes the weld is stronger than the base material, although it has undergone the same heating and cooling that the heat affected zone has. The reason why the weld retains strength is because the designers of filler rod add certain properties to the filler rod in order to make it strong or stronger than the base material after you're done welding. In order to get rid of the heat affected zone, I think I went over this in lab, you must heat treat the entire workpiece after you are done, which is one reason why you would use brazing. I briefly touched on this. So preheating. If there is any kind of water trapped in your weld, it can cause it to crack because the hydrogen will get into the internal structure of the steel or metal you are welding, and it will cause a dissociation, and it can propagate a crack through your weld, and it will happen really fast. If you weld over water, you can start to see a crack forming in 1 to 2 days after you weld it. So when you're doing any kind of tempering or quenching after you're welding, you must then reheat the material to get rid of all of the water and then weld over it. The thickness of material is very important when you are designing something or getting ready to weld it. Thin material tends to show more of the defective material properties or just inherent material properties more than thick. So stainless, for example, if you weld thin material, it will warp a ton, and it will be incredibly hard to weld. Yes. So this is a chart that looks super confusing, and this is just one of thousands of these charts. This is just pertaining to aluminum. So for each base alloy and filler rod, there are, and this is just half of the chart. The next half is on the other slide, the next one. But they'll help you understand the pros and cons of picking a certain filler rod or material. So based on a certain material that you're welding with, so 6061 aluminum, there's a certain range of acceptable filler rods that you can use. And if you were joining 6061 to something else, then there's a different set of filler rods that are acceptable to use in order to retain good material properties after you are done. They also talk about the ease of welding in these charts. So I don't know if you guys can even see anything on that chart, but essentially it goes over proper weld thicknesses in the first two tables for certain types of welds. It tells you how big the weld needs to be in order to have more strength in the material you're welding itself. And then underneath this last chart gives you the filler alloys and their strength in KSI and some tensile properties of the filler rod. This next chart, which you can't see it all. But you should look at when I send out the PowerPoint and learn how to read this chart, because it is very confusing at first glance. But once you figure it out, it's not too bad. The way it works is you find the material, the base material you were welding. If you were welding to a different base material, that top row is then where you find your second base material. You then follow them both down to the column, or the column and row where they intersect. And they will give you the filler rod number that you should use. And, well, they give you actually a number of filler rod options that you can use. And they give you A, B, C, or D rankings on how that filler rod reacts to certain properties. And the characteristics they go over are the ease of welding, strength of the weld joint when you're done welding it, the ductility of the metal, corrosion resistance of the filler rod you've picked, the strength at high temperature, so if it retains strength when it is heated, which a lot of metals do not, and how well the color will match if you were to anodize those two materials and the weld, because a lot of the times when you anodize it, if it is a slightly different kind of aluminum they use for the filler rod, it can show up as a different color. The shortcomings of the chart is it goes over no chemical composition information. So if you need to know if, let's say, aluminum at a specific alloy will react with another metal because of some additive, it does not tell you any of that. It gives you no heat or electrical conductivity information, which also varies alloy to alloy, and is very important for welding processes. And so here is a example of some chemical information about different aluminum and steel and how you rank them. So 6061, it starts with the number 6. So you would find 6 there. You then go over. It has aluminum, magnesium, and silicone in it. And those are the metals and that it is alloyed with. And so if one of those 3 metals is going to have non-favorable properties in the application you're using, you need to know about it. And then steel, it gets very complicated. There are many different kinds of steels, but the basics are that first number will denote the biggest components of what's in the steel itself. So like 7, the first number being a 7 implies it is some sort of tool steel because it uses tungsten to alloy it, and tungsten increases the melting temperature, increases the strength and hardness of the steel. However, then the second number in the designation will then be another chart that is giving you percentages of each. And yeah, it's essentially just how they achieve hardness in certain materials and desirable mechanical properties like conductivity or I guess conductivity for both heat and electricity, which are both present in welding, so you need to know that. Precipitation, hardening, I'll go over that for a second. So does anyone know what that is? No. So it's the change in the solid solubility with temperature, and it produces fine particles of an impure phase. And so what that essentially means is you have to specifically, it's more or less a heat treating process, and the grades of aluminum that say precipitation hardening means that you cannot work harden them. They will just break or become weak, so you cannot like use a hammer to provide more stress in the material. Even like bending and stuff will weaken those kinds of aluminum because that is a form of work hardening. And so you must use some kind of temperature and specific cooling rate in order to gain a harder kind of aluminum with those types. So a forming process can also influence the strength of the material that you start with. And so we've had experience with hot rolled and cold rolled steel. And this denotes the difference between the two. Hot rolled goes through hot, obviously, and cold rolled goes through cold. But a big difference between the two is the cost of the machines and the amount of equipment needed to make both. Hot rolling can be made with much less expensive equipment because it can go through 2 rollers and be decreased in size quite a bit, whereas cold rolling has to go through roller after roller, being compressed with a huge amount of tonnage. So the rollers have to be insanely big, and it can only be shrunk a little each time it goes through a roller. And yeah, hot rolling is weaker because it is formed at temperature and allowed to cool in air slowly, whereas cold rolled is stronger because while it is formed, internal stresses are added to the metal, which strengthen it. So here are some examples of common problems you can run into and should know about, because these are 3 insanely common metals used in welding and industry. So aluminum and copper, when you weld them, they have a very large amount of heat dissipation and electrical conductivity, so there's almost no internal resistance that the arc has to go through. So you need higher amperages in order to weld them because 1, there is low resistance through the workpiece. 2, while you are welding it, the heat wants to travel out in the workpiece. It does not stay localized to any one area, or as much as, let's say, steel. Stainless is one of my favorite metals, but it is a very low conductivity, so that's thermally and electrically, and a very high coefficient of expansion, which means that when you heat an area, the heat does not spread out over the whole workpiece, causing uniform heating like it might aluminum. And when you melt the stainless, it expands a ton and contracts a ton when you let it cool off. So you have very localized heating and contraction and expansion, which is the reason stainless warps so heavily, because there is a lot of internal stresses when it is a concentrated stress point. To avoid that, you essentially just minimize the amount of heat going into the workpiece while welding it, which is harder to do than it is to say. You have to be a very experienced welder in order to weld stainless and have minimal warpage. And it is also worth noting that depending on what you're doing, you might decide to weld much below the strength of the stainless. So put a very light, small weld on it to avoid having lots of warpage. So for example, when welding a handrail with a top plate of stainless steel and then posts, if you were to weld that at the strength of the material, what it would look like is this humping rail. So at each post, the stainless would be bending and then come up and then back down And obviously that's an exaggerated version, but it's like very apparent when you see it, because the welds here cause the bottom to contract and want it to bend over the post itself. And if you sight down a long run of stainless welded, you will see it do little jumps. And that's usually because, and they're little, because people are not welding that stainless stock to its maximum strength that it could be at. So they put very like surface level small welds if they're a good welder, to avoid having a ton of warpage. It's also worth noting that while welding stainless steel, you produce something called hexavalent chromium, which is extremely toxic to humans, and it will be in both a gaseous form and a solid form. It does not produce a ton of hexavalent chromium while you weld it in a gaseous form because it is toxic to breathe, but it's also toxic to ingest. So it is worth knowing that after you do a stainless weld, you should not cut that weld. So do not cut through that weld, and if you do cut through that weld, really be careful and wear a mask and then clean the area up after you are done, because that hexavalent chromium will be released from the weld while you cut it, and if you're using something like a grinder, it will be thrown into the air and you can breathe it in. I mean, it can cause long-term health effects. Galvanized steel has a very similar property in terms of being dangerous. You cannot really TIG weld it because of the zinc coating. However, while you are welding it, because the zinc melts at a much lower temperature than the steel underneath, you actually vaporize the steel as you weld, or sorry, you vaporize the zinc as you weld, and you form gaseous zinc oxide, which again is toxic to humans. And this one you really only have to worry about the gaseous form. So while you weld it, you need to do it in a very well ventilated area, or wear a very good respirator while doing it. And it is also worth noting that zinc, or galvanized zinc, contains a small amount of lead. And so while the zinc oxide will cause temporary sickness and really no like long-term health risks, the lead that is present in that gas can cause like brain cancer and a bunch of long-term health risks. So you got to be careful while welding galvanized steel. Sometimes worth just stripping the galvanized layer off before you weld it and then re-galvanizing it afterwards. And yeah, I think that's pretty much all I'm going to go over today. Before we go, so you guys are designing a project. If you have questions, I'm going to put my number on the board. You can just text me. I'm a lot more receptive to, or sorry, a lot quicker to responding to a text message than I am to an email. It also will help that if you have any confusion about Kevin or I or what's happening in lab, just shoot me a text. I'm happy to help, but you need to put your name and when you have the class so I know who you are. Yeah? So, if you want it. Monterey. Oh yeah? Right on.